Türkiye döküm sektörünün değerli temsilcileri, yeni bir eğitim ortamında beraberiz. Pandemi nedeniyle 1,5 yıl önce başladığımız webinarlarımıza gene webinar olarak devam ediyoruz. Ayda 2 kez webinar planlamaya çalışıyoruz. Bazen 3 oluyor. Ama şu ana kadar hiç aksamaksızın eğitim programlarımız devam etti. Kesinleştikçe sizlerle paylaşıyoruz eğitimleri. Önceden bildirme imkanımız olmuyor. Gene 2 haftada bir yaptığımız için webinarlara ya da ayda 2 kere. Bundan sonraki webinarımız 8 Haziran'da olacak. Haziran ayının ilk webinarı ve konusu alüminyum, tane inceltme ve modifikasyon. Bildiğiniz gibi Ankiros'la beraber düzenlediğimiz uluslararası kongremiz ertelendi. Gelecek seneye ertelendi. Bu sene için eğer bir ulusal kongre düzenlenirse yeri ve zaman konusunda sizleri bilgilendireceğiz. Şimdi bugün gene hepimizi çok yakından ilgilendiren sıcak bir konuya değineceğiz. Hatta 2 konuya, hem aşılama hem tretman, küreselleştirme Türkçesiyle. Bugünkü webinarımızı Elkem sunuş yapacak. Expert tercümesini yaptı. Ekranda Türkçe göreceksiniz. Sunuşlar İngilizce, ekran görüntüleri Türkçe olacak. Zorunlu hallerde Arif Bey veya Güroğlan Bey devreye girip katkıda Türkçe açıklamalarda bulunacaklar. Her zaman olduğu gibi chatbox dediğimiz alttaki sohbet kutusuna sorularınızı yazmanızı bekliyorum. Oturum sonunda ben kendilerine, konuşmacılarımıza soruları soracağım. Toplam öngördüğümüz süre saat 3'te bu etkinliği bitirmek. 3 sunuş olacak arka arkaya. İlk sunuşu Katrina Hartung yapacak. Kendisi aşılama teorisinden bahsedecek, ekranda gördüğünüz gibi. Daha sonra Matthias Lüben yüksek performanslı küreselleştirme tretmanı konusunda bize management tretman konusunda bir sunuş yapacak ve son sunuşu gene Katrina Hartung yapacak. Bu sefer bir dökümhanenin yüksek güce sahip aşılayıcılarla maliyetlerini nasıl düşürdüğü konusunda case study'ler, örnek vakalar paylaşacak. İlginç olduğunu düşünüyorum. Konuşmacılar girişte kısaca kendilerinden bahsedecekler. Onun devamında dediğim gibi her zaman soruları sohbet kutusunda yazmanızı bekliyorum. Webinar sonunda da mutlaka ayrılmazdan önce bizim bir tatmin anketimiz var. O tatmin anketinde doldurmanızı istiyorum. Katrin, it's your turn now. Please introduce yourself briefly and then start your presentation.
Thank you. So, my name is Katrina Hartung. I am a senior R&D engineer with Elkem, and I'm situated in Kristiansand, Norway, where we have part of our R&D facility. We started in Elkem in 1999. My background is physical metallurgist, and I've been working with cast iron and development of products or specialty products for cast iron in Elkem since 1999. So, and today,
yes. Please go on. Thank you.
And today I'll be talking to you first about inoculation theory. So, next slide, yeah. So to do that, we have to first say something about solidification of cast iron before we will then look at nucleation of the graphite. And then we will take a closer look at purpose and definition of inoculation after that. First, we need to understand the need for inoculation and inoculant in the production of cast iron. And to do that, we have to look at the iron-carbon phase diagram and how cast iron solidifies. So the simple picture is that cast iron is a two-component alloy with iron and carbon. You see the phase diagram to your right, and you see that you have an indication of a green line showing the cast iron side of the phase diagram with carbon above 2%, while the blue line represents the steel side of the phase diagram. So this phase diagram is actually representing two of the most common or most widely used materials in the world, cast iron and steel. So the areas that you see also here, the blue area is indicating the maximum amount of carbon that you can dissolve in the iron matrix, which is around 2%. While cast iron is typically the alloy from 2% up to around 4%. And then we come to the next point of interest in this phase diagram, which is represented by the pink frame, which is the eutectic point. And this is around 4.3, 4.2, depending on where they have taken their data from and how they have calculated or measured the phase diagram. So in cast iron, you can dissolve up to 2% carbon in the iron matrix. And this is where carbon or cast iron and steel deviate, where steel is predominantly or an iron phase. The cast iron has two phases. It has an iron-rich phase, which at the temperature of solidification we call austenite, and then it has a carbon-rich phase, which is making cast iron the interesting and maybe also tricky material, and also why inoculation is so important. So the cast iron solidifies with a eutectic transformation, which you see here in the pink frame. And we will take a closer look at this eutectic point in the next slide. So in this slide, we see, take a close-up of the eutectic point, and we see that this system actually consists of two. So the eutectic point represents the transition from liquid to solid. And for cast iron, what happens here is that a simultaneous nucleation and cooperative growth of the iron-rich phase, austenite, and carbon-rich phase takes place. Now in cast iron, the carbon-rich phase can either be graphite if it solidifies according to the stable system, which is here represented with the black lines, or it can solidify in the form of cementite or iron carbide if it solidifies according to the metastable system. A majority of the commercial cast iron grades rely on carbon coming out in the form of graphite to obtain the required properties, and the solidification according to the metastable system needs to be avoided. So from this iron carbon phase diagram, we see that the temperature window between the stable and metastable system is 4.6 degrees in this case, or around 5 degrees. But fortunately, cast iron is much more than iron and carbon. And a good thing about this element is that all these other elements that you have in cast iron is that they increase this window from around 5 degrees to around 60 degrees. So to avoid cementite, the solidification has to start and preferably end between these two lines that you see here. And the closer you are to the eutectic, the black line, the more safety you have for forming against forming carbides. And it is here that nucleation and nucleation potential comes in. Next. Now, the nucleation of graphite and cast iron will be heterogeneous as it requires less undercooling. With the temperature window indicated in the slide before, as it was shown here 5, but maybe with the chemistry that you will have a window of around 20, 40, maybe up to 60 degrees. It is not feasible to have a homogeneous nucleation, because a homogeneous nucleation typically requires more than 100 degrees undercooling before it can start. So both gray and ductile iron rely on heterogeneous nucleation of graphite. And during the heterogeneous nucleation, the graphite nucleates and grow from foreign substrate. This process requires less undercooling and is in line with the observation from thermal analysis and microscopy data that shows that you do have solidification taking place at a higher temperature and lower undercooling than 100 degrees, and you don't have a lot of cementite in the structure. Now, nucleation potential is then a measurement of the number of suitable substrate for graphite nucleation and says something about how easy it is to nucleate graphite. Next. And then this slide, we can see how the graphite in both gray and ductile iron is growing from these substrates. And the substrates are different in gray and ductile iron. This is not the purpose of us to discuss here. We go to next. So with inoculation, go to next slide. With inoculation, what we want to ensure is that as much as possible of the solidification is taking place within the stable system, giving us carbon in the form of graphite, either in the shape of flake, compacts, or nodules. The effect of inoculation can easily be seen and measured on a chill wedge, as shown here. In this case, I am holding different chill wedges from an inoculation trial in gray iron, and where we have used different inoculants on the same iron. And as you can see, there are different amounts of white in this chill wedge. The term gray, mottle, and white are reflected in the fracture surface and is a measurement of the amount of chill. So when I say white or a light area here in these fracture chill wedges, this is the carbidic amount of solidification. And the zone where you have a mixture of both gray and white is called the mottle zone. And where you have completely gray, there you have the stable solidification, or you have graphite coming out. So this fracture surface of a chill wedge is a very easy measurement that can be used for measuring inoculation or nucleation potential, as it gives you an instant response, and it can also show you differences between different irons or different inoculation. Well, next. Right. So you see the chill wedge here. Next again, press next again. Yeah, here are the different type of graphite or cast iron that we have, where graphite is growing differently. It's either lamellar, there's a compacted graphite, or the nodular structure. And the chill wedges are easy to use for gray and partly for vermicular. For ductile iron, you need to cut and polish them to see this same structure as you see here. Next slide. Click again. So in this slide, we will take a look at the principal effect on the cooling curve and microstructure of gray and ductile iron from inoculation. The cooling curve, which we can see here, come from thermal analysis. It's a time temperature curve of the solidification process. So phase transitions are here seen as arrests, and this curve can be used to evaluate nucleation conditions of the cast iron. Now the line TEG is the solidus line for the stable solidification, where carbon is precipitated as graphite, while the TEC is a solidus line for metastable solidification, where carbon is precipitated as cementite. So this reflects back to the phase diagram and the black and the orange line. So the TEG is the same as the black line, while the TEC is the same as the orange line. The one key parameter often looked at and which we have learned from the slides on solidification and nucleation is important, is the undercooling needed before solidification starts. This undercooling can be seen in the cooling curve as the temperature difference between the low eutectic temperature and the TEG line. And this is the low point that you see before it increases again and flattens out. So if you press again and again, and you see the vertical arrow represents the TE low, and you see that the inoculation lifts the curve. So instead of having solidification starting below the metastable line, the solidification is now starting between the lines. The other part that inoculation does is that it gives you a longer curve, so you have more carbon coming out as graphite when you inoculate compared to when you uninoculate. Should say that the blue line represents inoculated, while the black line, black dotted line here represents the uninoculated condition. And as you can see, before you inoculate, the structure looks either in gray iron, you have a mixture of undercooled graphite and better looking graphite, while in ductile iron, you predominantly have carbidic because your solidification starts below the metastable, while you get some nodules coming out. But predominantly it is undesirable structure. So the inoculation then, press next. Again, transform the structure from unacceptable to acceptable. And the purpose of the inoculation is then to change the structure from carbidic and undercooled to fully flake or spheroidal graphite. And this gives you the properties that you're after in the case of cast iron compared to a hard, brittle material, which is the result if you have solidification according to the metastable system. Next. So the goals of the inoculation is to avoid the formation of carbides and promote formation of graphite. You reduce the segregation and reduce shrinkage. You have improved machinability and a more homogeneous structure and properties throughout the casting. It reduces hardness and increased ductility. Next. So what is an inoculant? So by definition, an inoculant is an alloy which when added to cast iron, when it modifies the structure and thereby changes the mechanical properties. These alterations in the structure and properties can not be explained by the minor changes in the chemical composition of the iron resulting from the inoculation. So the difference with a good inoculant is that you can use so little that you do not change the composition of the iron itself. If you have to use considerable amount of inoculant, then you also will experience a change in the chemical composition, because normally the inoculants you use today or that are used are based on ferrosilicon or has silicon, and silicon will change the carbon equivalent of the iron itself. But if you have an inoculant that is highly effective, the addition is so little that it shouldn't change or should not have an effect on the chemical composition itself. Yeah. So I want to thank Emanuela and Bente Koka for helping with this. And this ends the first part on inoculation theory. Thank you.
Thank you, Katrina. Now, Arif, we will switch to other presentation, the second presentation, which will be presented by Matthias Lüben. Matthias, I will ask you again to introduce yourself briefly before presenting your study. So it seems that presentation is there. Please.
Thank you, Arif. Thank you. My name is Matthias Lüben. Nice to meet all of you, at least in a virtual way. I'm a foundry engineer located in the south of Germany, and I'm as part of the TCS responsible for the Turkish and German market. Today, I would like to present you some aspects of high magnesium treatment, high performance magnesium treatment. Arif, next slide, please. Well, just a quick look at the content of today's presentation. We will start with the nodularization process itself. Then we will compare different treatment methods. We will talk about ladle treatment methods and ladle and pocket design. I will show you specific treatment and cover alloys, and we will discuss at the end some case studies direct out of foundries. Please go ahead, Arif. Okay, as an introduction, a short glance on the nodularization process. Starting with the base iron on the left side, you can see the flake graphite. We are adding special nodularization agents like magnesium ferrosilicon or others with active elements like magnesium, calcium, or lanthanum. These elements tie up sulfur and oxygen and nodalize the graphite. But be careful, too high addition rate increases chill and shrinkage tendency and increases also the tendency to slag formation. The treatment alloy must be chosen adapted to the specific process. For example, to understand some influences, a too high magnesium content results in an increased reactivity and reduced magnesium yield. And another example, calcium, on the other hand, reduces reactivity and ties up also sulfur and oxygen, and it will give an inoculation effect. Calcium increases the magnesium recovery and the tendency to slag formation. Rare earth, on the other hand, ties up also sulfur and oxygen and nodularizes also the graphite. It neutralizes the subversive elements, reduces reactivity, and gives some inoculation effect. And finally, the use of lanthanum instead can reduce chill and shrinkage tendency. Next, please. Let's have a look at the efficiency comparison. Just a quick look at the upper left side. Treatments with high magnesium content or pure magnesium, like cord wire or the converter. The use will result in a violent reaction with lots of fumes and slag formation. We will have a low magnesium recovery and no inoculation effect at all. Arif, please one click. Thank you. Take a look at the green circle. Treatments with low magnesium containing alloys. It will result in a high magnesium recovery with proper inoculation effect. And the treatment will cause less fumes and slag formation. So at the end of the day, with a magnesium ferrosilicon treatment, you will achieve a high treatment efficiency, reduced fume and slag, a cleaner iron, superior metallurgy, low consumption of magnesium, reduced energy cost. You will improve your casting yield, and in the end, you will get lower reject rates. Next, please. Here you see a comparison of different ladle treatment methods. On the left side, the simplest approach, the pour-over treatment. In the middle, the sandwich treatment. The treatment alloy is covered with a cover alloy. We will talk about this later. And on the right side, the advanced treatment process, the Tandish cover. The ladle is covered with a lid, and at the bottom, there's a pocket for the treatment alloy and the cover alloy. Next, please. Some aspects on ladle and pocket design. An optimized ladle design achieves the following advantages. You will get a high recovery, as you can see, with a proper height to diameter ratio of 2:1. It is possible to achieve high magnesium recovery of about 80% with a consistent reproducibility. With this kind of ladle construction, there's no flare and about 90% fume reduction without any metal splashing. Minimum carbon and temperature losses are also achievable. Also important is an optimized pocket design. Please think of a sufficient volume per alloys and additional safety space for build-up. Ratio for the pocket of 1:1 or up to 1:1.5 between height and diameter of the pocket is recommended. Important is also a pocket without sharp corners, which is easy to handle to keep it clean. Next, please. Arif, please one click. Thank you. We will start with magnesium treatment alloys like Elmag and Lamet. At first, the Elmag nodularizer. They are available in extensive range of chemistries and sizes to suit every ladle and final iron requirement. Elkem is able to adapt the composition of the alloy direct to the needs of the customer's process. The Elmag alloy is a treatment alloy for specific applications in the foundry industry based on magnesium, calcium, and rare earths. The need of narrow product specifications to give highest consistency of magnesium recovery is self-evident. And the use of Elmag will improve nodal counts, nodularity, and structures. It is therefore cost-effective. Second, the Lamet nodularizer. The use of lanthanum as a source of rare earth in the alloy gives minimal shrinkage when compared to rare earth-free or cerium lanthanum-based magnesium ferrosilicon additions. It will increase the nodal count and nodularity with low chill tendency and minimize shrinkage. LAMID will ensure consistent casting quality with reduced costs. And as an additional information, production of these alloys is close to major casting clusters. Next slide, please. And again, one click. Thank you. Let's move over to our cover alloy top seat. A sandwich cover is recommended to obtain maximum treatment recovery. The purpose is to retain the alloy in the pocket for as long as possible before the reaction starts. Top seat addition compensates a negative effect of magnesium treatment. It will add further inoculation effect. This can be seen in thermal analysis curves. It stabilizes the metallurgical quality after treatment, providing more robust processes, and this is reflected in the structure and the mechanical properties of the casting. Top seat is available in two versions with 2 or 5% barium and in 2 different grain sizes, as mentioned in the table below. Top seat with barium is able to provide an effective management of the slag behavior. The result is a more clean iron, important especially for automated pouring equipment. The iron is less prone to promote slag and dross inclusions. Finally, it will result in a longer lifetime of the refractory. Next, please. Typical addition rates of top seat are 0.3 to 0.4% of top seat 5 for well-designed ladles and pockets, and a low magnesium containing FSM. About 0.7 to 1% top seat 2 is recommended for, let's say, poor designed ladle and pocket and a high magnesium containing FSM. To explain it a little bit, a poor ladle is a ladle with a low ratio between height and diameter, no pocket, or also a low ratio, or a pocket so tight that it's really hard to clean. A good, well-designed ladle, on the other side, has got a ratio of more than 1.5 between height and diameter. The Elkem recommendation is the ratio of 2. It also has got a well-designed pocket with a ratio of up to 1 to 1.5. No sharp corners and easy to clean. Next slide, please. Thank you. Let's move over to the case studies. Case study number 1. It is for a foundry with, they're using a high magnesium containing FSM together with top seat 2. If you have a look at the table, the reaction start has been postponed from 30 seconds to 45 seconds. There has been a reduction of FSM from 1.1 to 0.65% due to increase in the magnesium yield with an improved metal nucleation after treatment. Due to FSM quantity reduction and introduction of LAMID. The magnesium yield increases from 50% to 80%. The modification of the process increased the stability of residual magnesium and magnesium yield. Drier slags after treatment, cleaner iron, cleaner treatment ladles and pouring furnaces are also results. And do not forget, there's a reduced deslagging time. Next, please. Case study number 2. Again, the reaction starts later, so a more stable process. It started before the optimization at 14 seconds and now at 25 seconds. There's also a reduction in ferrosilicon magnesium addition from 1.15 to 0.7%, thanks to its improvement of the magnesium yield from 70% and now to 80%. The same metallurgy after treatment has been achieved, controlled by thermal analysis. Increased stability of residual magnesium and magnesium yield is also a result. And again, drier slags after treatment, cleaner iron, cleaner treatment ladles and pouring furnaces are results. And also, again, don't forget to reduce deslagging time, which is important for practice and foundry. Next slide, please. Case study number 3. A case study for a big open ladle with 15 metric tons capacity. The reaction start has been postponed a lot from 20 seconds to 50 seconds. There is a smaller reduction in FSM from 1.1 to 1.2% to now 1.0%, thanks to the improvement of the magnesium yield from 73 up to 8.1%. Same beta metallurgy after treatment has been achieved with a full offsetting of the influence of the treatment. And really important is that the customer was able to change from 3 products in ladle addition to 1. The ferrosilicon is still necessary because the customer is using base iron out of different furnaces. A reduction of 50% for DOS inclusions has been achieved. And again, because of the top seat, the slag is drier after treatment and the iron is much cleaner after deslagging. And also the result is for sure a reduced deslagging time. Next, please. Case study number 4. There has been a reduction of ferrosilicon magnesium from 1.3% to 0.9% due to increase in the magnesium yield. The magnesium yield seems to be low, but it is a very special process in a small historic foundry with kind of a 2-step treatment at temperatures of 1500 to 1530 degrees. At first, the FSM treatment is done with 300 kilograms, and then another 150 kilograms of melt is tapped into the ladle together with kind of an in-stream inoculation. And then the pouring is done completely manual direct out of this ladle. There's an increase in the magnesium yield from 35 to now 54%. An improved metal nucleation after treatment due to ferrosilicon magnesium quantity reduction and introduction of top seat has also been achieved in combination with increased stability of residual magnesium and magnesium yield. Also, the slag is drier after treatment. The iron is much cleaner. And also important, there's a significantly reduce of carbide tendency. Well, thank you very much for your attention.
Thank you, Matthias. That was short but comprehensive info. You have used your time quite good. So we have got time enough for Catherine for the second presentation. And then for the questions, we have got enough time again. Catherine, it's your turn again. Now, the topic is, again, inoculation.
Yes.
You don't need to present yourself.
Oh, I have presented myself, I hope. So now I will talk more about inoculation and how you can save costs with high potent inoculant, or what purpose the high potent inoculant can serve. So let's see. To the content of this presentation, we will start a little bit about melt quality, because that determines the job the inoculant has to do. And we will say something, have to say something about nucleation potential. We mentioned it, I mentioned it in the previous slide or previous presentation, where we went through the inoculation theory. We have to say something about the difference between gray and ductile iron, because they are different. And then I've tried to find some case studies, or I have some case studies in between. And we end up trying to summarize how, if you use high potent inoculant, how it can help you save cost. So let's see if how we go on time here. First, the melt quality or melting is actually what determines the melt quality. So the choices that you make when it comes to the raw materials, the time and the temperature you use, or the history of the iron, determines then the requirement for nodularizer treatment and inoculation. So it's like cooking. Make a good soup, you have to have good ingredients, and you have to have a good plan or a good recipe to make a good soup. Same with cast iron. So next slide. So the job of the inoculant is to ensure that the solidification occurs above the metastable line. And the closer it is to this the stable line, the black dotted line, the better the structure will be. Now here in this case, you see an example from our lab in Kristiansand, where we have 4 different irons. So the first iron here is uninoculated, and it's gray iron. And you see the actual curve with the actual structure. And as you're improving the inoculation, so going from the uninoculated to adding inoculant, but this can then be not adding enough, or a different type of inoculant will change how this curve places itself between the 2 lines. But all the purpose of the inoculant is that they should lift the line as close as possible to the eutectic, and it should stay, all the solidification should stay and end before you dip below the eutectic metastable line. But as you can see, with inoculation, the structure improves. We have to go back a little bit again on the iron. No, the next slide. So take a recap from first presentation and look at the phase diagram and the eutectic. And we have the 5-degree difference between the stable system, the black system, and the orange system, which is the metastable. So cast iron, luckily, consists of more than just iron and carbon. And all of them affect the stable and the metastable line. So they can either push these lines together or they can open them up. One of the most important elements, and which we know we have a lot of in cast iron, is silicon. Now, silicon is really nice because it opens up this window. So instead of having this 5-degree, then depending on the silicon level, it is from 20 to 60 degrees. So that gives you more time, or the iron more time, to get the nucleation started and to complete the solidification in time. So that's the recap to do. Next. And then we come to nucleation potential and thermal analysis. Now, thermal analysis can be used to read nucleation potential of a melt. I used a figure here from the article which is referred to in the top of this slide from Novacast. But thermal analysis is actually just a time temperature curve, as mentioned. And the different points in the curve have defined names and represents the solidification. The TL, the start of the liquidus, and the TE low is the lowest temperature before nucleation starts of graphite. And then there are different names of the different parts of the curve, depending on which kind of software you're using, or but the arrests and the different parts of the curve is the same regardless of which thermal analysis system that you're using. It's just that the slight difference in where the definitions or where the points are, depending on how the software smooths the curve. But the parameter we are that is of interest when it comes to nucleation potential is the TE low. And the TE gray here represents the eutectic stable line, while the TE white represents the metastable line. Now, the nucleation potential is then the temperature difference between the TE low and the TE white line, or you can measure it versus the TE gray line. Now, both TE gray and TE white are a product of chemistry, and you can be calculated if you have the chemistry. But TE white can also be determined by using a tellurium cup, and you can always pour a white cup or a tellurium cup, and you will have the TE white. So the nucleation potential can most easily be measured versus the TE white in a foundry. And then a large temperature difference between T low and T white means a good nucleation potential, while a low temperature difference means a poor nucleation potential. This means fewer nucleations, possible nucleation substrates for the graphite to grow on. Next. And then to the difference between gray and ductile iron. Now in gray iron, the nucleation condition improves with increasing carbon and carbon equivalent. You can say that gray iron is actually a self-inoculating material, or the inoculation condition improves with increasing carbon and carbon equivalent. This is represented here on the curve to the right, where you have a representation of the liquidus temperature, which is the line, the line that crosses and down to the stable eutectic temperature. And then you have the delta T is the undercooling after inoculation, and delta T0 is the undercooling needed before you inoculate. And as you see, the undercooling before inoculation in gray iron improves with improving carbon equivalent. So as a result of this, it is expected to see a decrease in undercooling needed to initiate graphite nucleation with increasing carbon in gray iron. And TE low as a result of this will also increase with higher carbon and higher carbon equivalent. So ultimately, a gray iron, where a high strength gray iron will typically have lower carbon content or carbon equivalent, and will therefore have more undercooling because you are more to the left in this diagram, versus a high carbon equivalent, or the irons, gray irons that are should transport a lot of heat, or like the brake discs, or have a high damping capacity. They will typically have higher carbon equivalent and will also have a higher or better nucleation condition to start with compared to the high strength gray irons. But for ductile iron, the situation is a little bit different. Matthias mentioned or showed some example of magnesium treatment. So, and this is the differentiating thing between gray and ductile iron. To make ductile iron, you need, or you do, an additional process, the magnesium treatment, which ties up sulfur and oxygen. And it does that to change the graphite growth from flake to nodules. To have the graphite growing as nodules, you have to remove sulfur and oxygen and other impurities. Now, naturally, ductile iron will also be, from the charge mix or from the charge setup, lower in sulfur. If not, you would have to add more magnesium ferrosilicon. So this addition, or this process step with the magnesium, is removing effectively a lot of nucleation sites and makes it more difficult to nucleate graphite in ductile iron than gray iron. As a result of this, the undercooling observed in ductile iron before you do an inoculation will almost always be below this metastable. And that's why you have carbides or carbidic structure if you do not do any inoculation after magnesium treatment. So in ductile iron, the need for inoculation is independent of chemical composition. Next. So we come to our first example where we compare superseed versus foundry grade ferrosilicon. I think one of the most popular inoculants in gray iron production is just ferrosilicon, or foundry grade ferrosilicon. The other very popular inoculant used in gray iron inoculation is superseed, or strontium containing inoculant. And in this slide here, we see a comparison of superseed versus foundry grade in two types of gray iron. So one with low carbon equivalent, would see around 3.9 to the left, and one with 4.4 to the right. So you have what we call low or hypo and hyper or eutectic gray iron. And as we have then show the different parameters which we typically associate with nucleation and inoculation, which is chill. And then we have the most common thermal analysis parameters used. They have the TE low, we have the recolescence, the graphite factor 1, which is the length of the curve. I believe in the EPIC or Elkem thermal analysis system, this is the equivalent to the LET to the, is it ST? And the graphite factor 2 is the angle at the end. So that's the angle at the end of the solidification curve. Then we have the solid dust temperature. And then we can see the example here with supersede versus foundry grade of ferrosilicon at the low carbon equivalent. You have lower chill, about 1 millimeter. You have a higher, lower eutectic, lower recolescence. There is not much difference in the graphite factor 1 and graphite factor 2, and TS is the same. But the two main parameters, so the main parameters chill and T low, are in favor of the supersede, providing a better nucleation condition. So supersede is better and a better inoculant than foundry grade in this circumstance. If we then go to the case to the right, where you see a higher carbon equivalent, you see, first of all, that the nucleation potential is better in the iron to start with, or you have higher parameters. All the parameters look better because you already have improved the nucleation just by having changed the chemical composition. So your TE low is higher compared to the lower carbon equivalent iron. As a result, the chill you measure is lower both for supersede and ferrosilicon. And the recolescence is lower. You have a higher graphite factor 1. You have a longer time in which the graphite is precipitating. And of course, more graphite is precipitating as a result of this, that you also have more carbon available. And a more favorable difference between the graphite factor 2 and graphite factor 1. You would like to see a low graphite factor 2 and a high graphite factor 1. And the solidification ends at a higher temperature in both cases, suggesting that your solidification ends with a greater safety versus the metastable temperature. And you should have more good looking or the right type of graphite in the case of the high carbon equivalent iron compared to the lower equivalent iron. But in both cases, you will see that supersede is a better inoculant than foundry grade at the same addition. So what you could do then is that you could reduce the supersede addition to make them perform equal. Now we go to the next case example. So supersede inoculant was developed specifically for high strength gray iron back in 1966. So at that time, the inoculants that were used were ferrosilicon or high silicon ferrosilicon, or it was this SMZ type inoculant. But for all of these inoculants, you had to add quite a lot of them to have the chill reduction. And then by having a larger addition, then you also change the chemical composition. So the supersede brought with it that the possibility to add considerably less. But remember, at this time, the dominating inoculation method was also ladle inoculation. Today, we are stream inoculating. But still, it is designed to give maximum chill reduction with lowest possible addition and thus minimum additional silicon. So you're retaining the maximum amount of strength you can get from the chemistry of the gray iron, because in gray iron, it is predominantly the carbon equivalent that will determine what kind of strength the iron has. And you use silicon to offset the formation of carbides in the solidification, but at the expense of a higher risk for shrinkage. So this was a very successful product when it was launched, and we today see a lot of different strontium containing inoculants from a lot of different suppliers. So Elkem did a benchmark study on this. We collected different superseed copies or superseed alternatives from all around the world. And we did a trial in-house in our lab using hypo-eutectic iron, so similar to what you saw in the previous case, the low carbon equivalent. We tested then all the different inoculants that we could get hold of against our superseed. And in this case, you see here an example where we have tested with 2 of them, presented together with the results for superseed, and where we have varied the addition rate. So in the figure, the left figure, we have inoculant A versus superseed, and as a function of addition rate. So at the 0.1 addition, and we are adding this in a ladle, a small ladle, and hold it for about 1 minute before we pour it. So it's equivalent to a ladle addition. But the 0.1 in a ladle addition is then not a very high addition compared to what we see in foundry operation. So then at 0.1, we see that the inoculant A performs similar to a superseed. But what happens then at lower addition, if we reduce the addition from 0.1 to 0.05, we can see that there is a slight increase in chill with superseed, but a quite considerable increase in chill with the inoculant A. So this indicates that superseed is a more effective inoculant than inoculant A, and same effect is achieved with a much lower addition, can be achieved with a much lower addition of superseed. So in the right figure, we are looking at another inoculant. But here we can also see at the 0.1 that there is a difference between superseed and this inoculant. Now, one way that you can, with a foundry, or that you can equalize differences in the performance of inoculants is to just increase the addition rate. So then we have increased the addition rate for inoculant B, and we see even at 0.15 addition, you cannot get to the same level as 0.1. And interestingly enough, even at 0.05 superseed, we know that this superseed is a good inoculant and you can reduce it. So even at 0.05, this superseed behaves better than inoculant B in this case. So this case here shows that in some cases, increasing inoculant addition can even out performance. This you can with inoculant A, you can increase it to 0.15 if you want. But remember then that you have to reduce the silicon level to compensate for this silicon addition you make here. And silicon in the furnace is cheaper than silicon as an inoculant. So it's better to put the silicon units in the furnace than adding them later in the process. So it also shows that, I would say, some inoculants are just better and provide more consistent performance regardless of addition rate. So that's what you want from an inoculant as well, and what the high potent inoculant is providing. It's providing a better addition, a better performance at the lower addition, and a consistent performance at varying addition. So this hopefully shows the strength of superseed, and superseed is also a product that is developed for inoculation of high strength gray iron. Next. Now, Matthias showed some interesting examples on magnesium treatment, and you also saw the mentioning of different types of magnesium ferrosilicons. And as mentioned before and known, ductile iron has a higher need for inoculation than gray iron. This is because the magnesium treatment alone cannot provide sufficient suitable nucleation sites. But there is difference in what kind of nucleation sites you can generate or could potentially generate from a magnesium treatment. And in this slide, we can see an example of how different the nucleation conditions can be with different magnesium ferrosilicon qualities. So here we see the structure and polished and etched condition of samples that we have collected from trials in our lab using different magnesium ferrosilicons. The one to the left is the magnesium ferrosilicon without rare earth, very commonly used in Europe. The one in the middle has some rare earth, while the inoculant or the magnesium to the far right is a LAME type magnesium ferrosilicon. And as you can see, the two inoculant, or the two examples to the left, both of them have passed below the metastable. So you have carbides in the structure and very poor graphite. While in the case of LAMET, you're actually been able to have the solidification between the metastable and the stable line, and you do not have any carbides. So of course, the amount or the need for inoculation is very different depending on which magnesium ferrosilicon treatment you have started with in this case. So this composition of magnesium ferrosilicon can significantly affect nucleation condition in ductile iron and the need for inoculation. Next. So we go to an example in ductile iron and look at the difference in performance of reseed and foundry sill. So foundry sill is a calcium barium inoculant, which can be used for both gray and ductile iron, while reseed is a cerium-containing inoculant specifically developed for ductile iron, and especially ductile iron treated with pure magnesium or where there is low sulfur and oxygen after the treatment. So where you have a high need of an inoculant and a good performance of the inoculant. So for ductile iron, it's common to look at nodule density and nodularity along with the thermal analysis. So we don't look at chill levels, although we could do that too, but it's not primarily how you measure the nucleation performance. So in this case here, we see that the reseed is providing a higher nodule density and nodularity compared to foundry sill. In this case, the iron in question was a solution strengthened ferritic ductile iron of the type 610. And the main thermal analysis parameters are also better with reseed than foundry sill in this case. So you see a higher TLO, you see a higher TS specifically, and the recoalescence is lower. For these SSF irons, the solidification is different than the typical ductile iron, so the graphite factor 1s and 2s are not always as good as you can see with your standard ductile iron. But what you can see is here that for the graphite factor 2 is at least lower for the reseed type. It is not always so easy to use these parameters. But as a result, at the same addition rate in this case, reseed is providing 50% higher nodule density than foundry sill, and the nodules are looking a lot better. Next. So in this last example, we are looking at the results from a stress test of ultraseed versus SMZ in ductile iron. By stress testing, what is meant here is that we're trying the inoculants at different inoculation additions. So we try to go really low in ductile iron. I think you would agree with me that 0.05 weight percent addition in ladle is a very low addition for ductile iron. And then we have different addition rates. And I should say also at the same time that we are adjusting, so the final silicon is the same. So although we have different addition rates of the inoculant, the final silicon is the same. We are also doing this with an iron we know is tough. So the composition here is for a 500 iron. So we can use the ferrite content to measure, have a good measurement of the nucleation. So we see instantly then if we have more nodules or differences in nodule densities, that we see it on the ferrite light ratio. But we have also used the rare earth free inoculant or magnesium ferrosilicon in this case, because we know that in this case, the inoculant has to do the maximum amount of work. So if we want to stress test something, we use this as a good basis. So, and as can be seen here, the ultraseed is providing a higher nodule density at a lower addition than for SMZ. So the overall nodule density is low because this is, as I said, this is a tough iron. We have made it tough. We would probably have to have a higher inoculation addition, but we can still see the difference between the inoculant from 0.05 And 0.1, 0.15, you have to be up to 0.2 weight percent of the SM set to come close to the ultraseed in nodule density. Similarly, on the ferrite content, for the lowest edition of SM set, we have carbides in the structure, while we don't have carbides at all with the ultraseed. And we have a consistently higher ferrite amount with ultraseed. You see the same trend with the TE low as you see for the nodule density. So with increasing inoculant addition, your TE low is improving. So, and here the ultraseed is also better than SM set, all the way up to 0.2, where they become more equal. But this shows, and I should say that SM set was one of the first inoculants that were developed or patented, but this was originally an inoculant that was developed for high strength gray iron. So it was available when ductile iron was developed or invented, but the inoculant itself is older than ductile iron. So it was there, but it was never developed or never really designed to work in ductile iron. But ultraseed cerium, however, was specifically developed for ductile iron and specifically for ductile iron with poor nucleation potential. And it is designed to provide good performance with minimum addition and to allow the foundry to operate with high carbon equivalent in silicon in the furnace, so that you can have just a small inoculant addition and have packed all your silicon units in the furnace where they are cheaper. So to the last slide. So how can you save, or how can high potent inoculants save costs? So the high potent inoculants are developed to provide specific benefits. So you should be looking at the specific benefits that you might have. And there are some inoculants that are specially designed for gray iron, those that contain zirconium or strontium, zirconium, or aluminium. Or in ductile iron, they will typically have cerium, bismuth, sulfur, and oxygen in order to be more effective. So these are inoculants that are then designed to work specifically for that need. For gray iron, for instance, having only working with strontium, zirconium, you have often a very, very clean inoculant. They come with low calcium and in some cases also low aluminium. But too low aluminium in gray iron is also not recommended, as aluminium is an important part of the nucleation sites. More effective means that they allow for use of lower addition and provide more consistent properties. This again leads to less impact on chemical composition. It is more of the composition that you have put in the furnace, so the more of the silicon that you have put in the furnace, the more you can save on alloying addition. This in turn means lower cost because you can run your base iron closer to final iron composition, which leads to lower wear on your lining. If you run higher silicon in the furnace, your wear on the lining is less. Most of the cast iron is produced in induction furnaces with silica lining. And if the iron is low in silicon, it means that you're eating off the lining. If you run higher silicon, then you are maintaining the lining or maintaining a longer lining life. It would also allow you to use more returns if you make ductile iron. Returns will have higher silicon than your steel or your pig iron, depending on where you buy it from. But you can then use more of your returns if you have a lot of it, and especially for ductile iron, that there's generally lower yield in ductile iron production than in gray, so you have more returns available for use. And this is also provides you with an iron that will naturally come from the furnace with the overall lower need for inoculation. So that you can run lower carbon equivalent in your gray iron. That's another way to save cost. That will allow you to use more steel scrap, and which will allow you also to use less alloying to achieve same strength. If you can adjust or control carbide or the carbide tendency in your gray iron with a good inoculant, then you can work with a lower silicon and lower carbon equivalent in your gray iron. And you get your strength from controlling carbon equivalent instead of using alloying elements. And alloying elements tend to be higher in cost than carbon and silicon. So you may be able to use less alloying to achieve the same strength. So also relying on high potent inoculant or using high potent inoculant means that you are more flexible in the use of raw materials. You have more, you can play around with the choices on raw materials more in the base iron because you have an inoculant that you can rely on and small addition late. You may be able to run cheaper raw materials and use less alloying. If an inoculant is good and you can use less of it, then you can also cut back on alloying. Normally, these high potent inoculants are designed to provide specific benefits or help to reduce defects. So of course, if you reduce those defects, you have a reduction in scrap rate. So your metal yield improves, and that improves your overall cost situation. By having more consistent properties, also you have more uniform machining. And more uniform machining means less variation machining cost and wear on machining, and then you save on the machine. It should be said at the end, although, that all inoculants will work. It's just a question of how much you need and how consistent the performance is and how forgiving the inoculant. So it's important when you select an inoculant is maybe to look at the worst possible condition that you can have and see which inoculant can help you in this condition. And that should, then you should look at and see, is this condition, can I do something with this condition? And see. I hope this gives you some idea on how you can save cost. And it's not just by looking at the cost of the inoculant itself. So the money you save on the choices, on the choice of using a high potent inoculant and how you actually build up your entire process from the charge material, the choice of magnesium ferrosilicon, is part of how you save eventually the cost on the inoculant. Yeah. So I think my colleague, Landa, Manuel, Torbjørn, and Alberto for this help with this presentation. And Bente Boka, our technology department, would help on the nice images of the structures. Thank you.
Thank you, Katrina. That was good. That was the last slide, especially, was summarizing almost everything. We have to use less but effective inoculants. Değerli katılımcılar, sunuş burada sona eriyor. Şu anda anket gelecek ekrana. Anketi cevaplandırabilirsiniz. Ben Gürolan Bey'e sonradan katıldı. Gürolan Bey'e bir söz vermek istiyorum. Gürolan Bey, bir özet yapmak ister misiniz bu sonuçlar üzerinden? Süreden bağımsız. Vaktimiz var çünkü.
Ben herkese katılmak için teşekkür ediyorum. Tabii sevindirici olan bizim Elkem olarak zaman zaman rekabet içerisinde olduğumuz şirketlerden de mühendislerin katılmış olması. Demek ki Elkem'in sektörde anlattığı şeyler herkes tarafından ilgi görüyor. Bunu görmek sevindirici. Biz biliyorsunuz ertelenmeseydi bunu kongrede de gerçekleştirmek istemiştik, benzer bir şey. Ama bu webinarın da ben açıkçası yararlı olacağını düşünüyorum. Ama tabii webinar dışında daha ayrıntılı her türlü soruyu cevaplayabilecek olan uzmanlarımızı biz özellikle davet etmek istemiştik. Dolayısıyla buradan bağımlı kalmayıp kendi firmalarına özgü bir takım problemleri de bize iletebilirler. Biz Arp ile beraber bunların gerekli cevaplar alınması konusunda da elimizden gelen bütün çabayı da gösterdik ve gösteriyoruz. Teşekkür ederim.
Ben de bir iki şey ilave etmek istiyorum. Öncelikle herkese teşekkür ediyoruz katıldıkları için. Gürulan Bey'in de belirttiği gibi biz saha çalışmalarında müşterilerimize, dökümanelere yardımcı olmaya çalışıyoruz. Bizim yetersiz kaldığımız durumlarda bu sefer Elkem'in uzmanlarına başvuruyoruz. Hatta diyelim içinde çıkılmayan durumlar veya çözülemeyen problemleri varsa numunelerini göndererek Elkem'in gelişmiş laboratuvarlarında detaylı analizlerini de yaptırabiliyoruz. Böyle de bir Elkem'in gerçekten güzel bir hizmeti var. Bunu da belirtmek isterim.
Şimdi değerli katılımcılar, hiç soru yok. Soru sormanızı bekliyorum ben. Aşağıdaki sohbet kutusuna soruları cevaplandırmak için vakti var. Uzmanlarımızın. Evet, bir şey var, bir yorum var. Her zamanki gibi soru sormak istiyorum diyor. Bu sunumlara ilerleyen tarihlerde ulaşabilecek miyiz? Evet, ulaşabileceksiniz. TÜDOKSAT Akademi'nin bütün webinarları kayıt altına alınıyor ve daha sonra TÜDOKSAT web sitesinde ulaşıma açık. Bir sınır yok. Webinarlar kayıt altında, onu söyleyeyim. So, Matthias, Katrina, no questions that shows two things. One of them is either the topic is too simple or too difficult. What's your comment?
Could you repeat this?
Since there is no question to your side, either your presentation was too clear, everything is understandable, or it was too complicated that nobody is able to ask any question.
I hope it wasn't too complicated. Yeah, let's hope it was clear.
Let me ask you a question. Let me ask you one question. Once upon a time, we were using a term called undercooling quotient. Undercooling quotient was the ratio of undercooling temperature after inoculation divided by undercooling temperature before inoculation. And this quotient was giving us info about the effectiveness of inoculation. But you did not mention anything from this. Could you mention? But before answering my question, I need to translate it into Turkish for my colleagues. Okay? Değerli katılımcılar, bir soru sordum. Kendisinin sunuşunun bahsetmediği şeyde bir undercooling quotient dediğimiz aşılama katsayısı olarak tercüme edilebilir. Aşılama etkinlik katsayısı olarak tercüme edilebilir belki Türkçe'ye. Aşılamadan sonraki undercooling temperature'ı aşılamadan öncekine böldüğümüzde bir rakam bulunur. Bu rakam 1 ise benim hatırladığım kadarıyla anlamlı, birden yukarıda olması lazım ki aşılama etkin olsun. Aksi takdirde aşılama etkin değil diye. Şimdi kendisinin cevaplandırmasını bekliyorum. Bu arada sorularınıza geliyor. Ben de bir yandan onları okumaya başlayayım. Yes, Katrina, please.
Yeah, so using a quotient, you do that to some extent by using the white. So if you have a white cup, you will establish this undercooling if you have no inoculation. So you have to, how do you say this? For using a quotient, you need to have a reference point. And if you're working with a gray, the reference point changes depending on the chemistry. So I think maybe that's the reason why they have left this, the quotient, the relationship. You could do this also with the way that I presented it. It's just that you then you use the TE low value you get from the white curve, and then you divide the TE low from the gray, what you measure. That would be the same as the quotient that you're talking about. But instead, and the difference would be, as you say, it's a quotient. It's the difference from where you are in the white and how far above is the gray. So in fact, you are using the difference between the two temperatures, but you're not dividing. I don't know if that explains it a little bit, but the quotient would mean that you could more easily compare different irons.
Thank you. Thank you. Güroğlan Bey, siz tercüme eder misiniz? Ben kısaca anladığımı anlatayım.
Sorry, Saifi, if I am able to add something. I used to work with this undercooling quotient in the past. I know this work of Professor Döpp and Dr. Kasper. It's an old German work a few decades ago, I think, maybe 30, 40 years ago. And this quotient is, in my opinion, only good to use if you compare different irons in one process. It isn't possible to compare different processes because, for example, if you are using this quotient for a pure magnesium treated iron, the factor is way out of line, and but for sure it is possible to inoculate this kind of iron. But like I said, this quotient is only possible if you are really comparing one stable process for different irons.
Thank you, Matthias. Yeah, that was a term which was commonly underused about 30-40 years ago.
Yes.
Değerli katılımcılar, bir ekranda
sanırım 3 tane soru var.
Undercooling temperature'ın eğrisini gördünüz. O ikisi arasındaki fark da aynı anlama gelir diyorlar. İlla bir katsayı olması gerekmez. Eğer bir katsayı kullanılması gerekirse bununla ilgili bir referans olması gerekir. O referans olmadığı için, yani çok ideal koşullarda bir ölçüm olmadığı için bu belirli bir dönem kullandıktan sonra kullanımdan kaldırıldı. Şu anda bahsedilmiyor deniyor benim sorum için.
Aynen.
Güroğlan Bey, Arif Bey, siz şeyi görüyorsunuz değil mi? Sohbet kutusunu görüyorsunuz.
Sohbet kısmında 3 tane soru var.
Evet.
İsterseniz
bir tanesi Metin Demircioğlu'ndan geliyor. Metin Demircioğlu
questions coming from Metin Demircioğlu.
Yeah.
Could we make a comparison between the standard treatment methods and wire treatment? Is there any difference in the risk of shrinkage? Who will answer this question?
Can you please repeat the question? It was a little bit interrupted on my side.
Okay, let me repeat it again. The question is coming from Mr. Metin Demircioğlu. Could you make a comparison between the standard treatment techniques, standard treatment for the modularization, and the cord wire treatment? Is there any difference in shrinkage risk in terms of these treatment techniques?
Güroğlan Bey, sizin mikrofonunuzda veya bağlantınızda bir zayıflık var. Sesiniz biraz dalgalı geliyor, anlaşılması zor. İzin verin, ya Arif Bey veya ben tercüme edeyim.
Ben sorayım tekrar.
Tamam, siz tercüme edin.
Lütfen Arif Bey sorsun.
The question is, what is the difference between the cord wire treatment method and the normal treatment method? And which one gives the higher shrinkage risk?
Alberto is raising his hand, sorry.
Yeah.
I don't want to interrupt you, Katrine.
Yes.
Okay.
Alberto, yeah, now you can talk.
Maybe I can reply to this question. Of course, it is a bit too open question because it depends on the type of ferrosilicon magnesium, the type of the core wire. Generally speaking, we can say that with the core wire, we destroy more the nucleation level of the base iron. Mainly with the core wire containing pure magnesium side, so blend or mixed, etc. So generally speaking, the core wire treatment is more destructive for the conditions of the base iron, and with the standard undiscovered treatment, etc., we can achieve a better performance in terms of shrinkage tendency. This, let me say, the 99% of the cases. And the reason is because the Danish corner treatment destroy less the level of quality of the base iron in front of the core wire treatment.
Ben kısaca açıklamaya çalışayım. Şimdi biz kendimiz de öncelikle hani katkısı olur diye söylüyorum. Biz expert mümessillik olarak hem manizum satışı yapıyoruz hem de bunların saha çalışmalarını da yapıyoruz. Dolayısıyla tabii uzun yıllardır da Elkem'in ürünleriyle bu tip çalışmalar yapıyoruz. Açıkçası hani hangisinin daha iyi performans verdiği konusunda bizim de bir takım tecrübelerimiz var. Alberto'nu da söylemeye çalıştı. Yani yüksek magnezyum içeriğinden dolayı tel magnezyum, çünkü en az bu iş %20-25 magnezyum içeren ürünlerle yapılıyor. Dolayısıyla yüksek reaksiyon şiddetinden dolayı metali daha fazla yıpratıyor. Hem çekinti riski azalıyor hem de o yüksek reaksiyon şiddetinden dolayı magnezyum verimi normal magnezyumlara göre düşüyor. Böyle bir şey var. Tabii bunun sonucunda da çekinti riski tel magnezyuma göre her zaman tel magnezyumda daha yüksektir. Dolayısıyla daha yüksek potansiyelli bir aşılayıcı kullanmaya ihtiyaç vardır eğer tel tretmanı kullanıyorsanız.
Katrina, the question is coming from Kamil Büke, and he is asking that if we use high quality inoculant, not only in gray iron but also in ductile iron melting, is it possible to reduce peak consumption on the charge makeup, which could be replaceable with the steel scrap?
Yes, but you need to do the full. You need to look at the full process. But high potent inoculant can be used to do that. So if you're using more steel scrap and taking out the pig iron, what normally happens then is that the iron from the base iron can be tougher to or will have lower nucleation potential. But you can fix that if you look at the combination of magnesium ferrosilicon plus the high potent inoculant. So you can compensate for this. So, but maybe not the inoculant 100% alone can fix everything you do on the steel. But I'm sure that looking at the combination of what you do on the charge plus the treatment process, you can fix or make it forgiving to more steel scrap.
Değerli katılımcılar, Kamil Bey'in sorusuna cevap evet olarak geldi. Özellikle sizlere de önerilecek bir yöntem. Eğer nitelikli bir aşılayıcı kullanılırsa Sfero'da ve gri dökme demirde tabii daha fazla çelik hurda kullanarak, daha az pik kullanarak maliyette bir tasarruf sağlanabilir. Onun cevabı evet. Ancak tabii bugünkü koşullarda değişen ne diyelim pik, saç, pik, çelik hurda maliyetlerinde bu şeyi hesaplamayı çok sık yapmanız gerekecek. Teknik olarak mümkün, evet. Ne dersiniz Arif Bey?
Ben de bir şey ilave etmek istiyorum.
We have a lot of customers not using pig iron in the ductile iron production, or using only 10% of pig iron just to wash the trace element. And thanks to the right inoculation chain from the furnace to the pouring, they can produce very good castings, very good iron in the, for instance, also in automotive market. From 0, maximum 10% of pig iron. They are producing a lot of iron per day. Very good.
Ses gidip geldi. Ben tam anlayamadım ama duyulmadı.
Ben de tam anlayamadım ama sanki sıfır oranına kadar pik kullanmak mümkün. Yani tamamen hurdadan eritmek mümkün ve orada tasarruf daha büyük olur gibi bir şey anladım ben. Evet. Siz şeyden bahsedin.
Ben şöyle bir ilave yapmak isterim. Dökümhanelerde daha çok böyle yüksek pik kullanımıyla daha kaliteli döküm yapılabilir gibi bir algı var. Aslında bu tam doğru değil. Mesela belli oranda pik, yani yapılan saha çalışmalarında %20-25 oranında pik kullanımı ve geri kalanı prosesin getirdiği işte yolluk oranı da ilave ederek geri kalanı çelikle tamamlayabilirler. Çelik fazla kullanmanın aslında avantajı var. Baz metalin çekirdeklenme potansiyeli üzerinde. Neden? Çünkü çelik yüzeyi, hurdanın yüzeyi oksitlenmeye daha müsait. Daha fazla oksitlenme alanı sağlıyor. Dolayısıyla ne kadar çok oksitlenirse bir şarj malzemesi çekirdeklenme potansiyeli çok daha artar. Dolayısıyla devamındaki aşılama ihtiyacı o oranda düşer. Yani daha az aşı ihtiyacı ortaya çıkar. Dolayısıyla hani yüksek oranda pik kullanmak bazen tam tersi daha fazla aşılayıcıya ihtiyaç duyabilir ve çekirdek olarak da sonuçta pik dediğimiz şey bir aslında ölü metaldir. Sonuçta o da dökümden gelen bir şeydir. Onu tekrar canlandırmak için ön şartlandırıcılar vesaire kullanmak gerekiyor o şeyi. Ama çelik kullanıldığı zaman o biraz daha taze bir baz metal ortamı sağlıyor. İçeri giren oksijen ve kükürtten dolayı.
Matthias, a question is for you from Faruk Sezer. He is saying that on ferrosilicon magnesium, if we use top seed or a similar inoculant as a cover, what is the effect of this inoculation? Does it affect the final inoculation, or does it badly affect the shrinkage tendency?
It does affect for sure the complete inoculation process. As my colleagues mentioned before, we're not supposed to look at only one single step at the process. We have to check the complete process. And if we're adding, for example, top seed with barium-containing as a barium-containing cover alloy, it is for sure influencing the total nucleation process. And there's no, to add something, there's no bad effect. Just speaking for the top seed.
Ses girip geliyor, anlamadım, bilmiyorum. Ses.
Şöyle diyeyim ben anladığım kadarıyla aktarayım. Ses gerçekten anlamak biraz zor. Kulaklıkla konuştuğu halde gayet net olması lazım. Evet diyor, arkadaşım da bahsetti, Katine de bahsetti diyor. Önemli derecede etkiler diyor. Bunun aşılamanın Tretmanla birlikte yapılması, örtü malzemesi olarak aşılayıcı kullanılması ve aşılama ve Tretmanın birlikte yapılması aşılama sonuçlarını etkiler diyor.
Bir ilave yapabiliriz. Tapsit baryum içeren bir üründür. Baryum biliyorsunuz özellikle sıfır dökümde aşılama etkisi yapan temel elementlerin başında gelir. Dolayısıyla ön aşılama etkisi vardır. Bir sonraki aşamada aşılayıcının miktarının da azaltılmasına katkı sağlar. Tapsit kullanılımı.
Okay. Katina, there's a question from Gökhan Yıldırım to yourself. He's saying that on gray iron, there is a top limit for inoculation amount, which should be minimum. But is there a top limit for ductile iron inoculation?
I'm not sure I would say it's a top limit for inoculation, but there is a top limit for carbon equivalent in ductile iron. So once you should avoid adding so much inoculant late that your iron becomes hyper-eutectic in behavior. And that sometimes foundries forget to calculate in this late silicon addition, because and even 0.1, 0.2 can be enough to make your iron behave hyper, and then you get large nodules and you get increasing shrinkage tendency. So it's not that the inoculation has been incorrect. It's just that the carbon equivalent is not correct anymore.
Evet. Arif Bey, siz söyler misiniz? Ben anlatayım.
Şimdi aslında aşılayıcı ihtiyacı Baz metal ilgili gene doğrudan yani bunun için hiçbir zaman bir sınırdan bahsedilemez. Yani az veya çok şeklinde. Çok yüksek aşılayıcı Tretman'in de dediği gibi o zaman öteklik noktasını yükseltir ve çekinti eğilimini arttırır. Yani yüksek high öteklik şeyini yükseltir. Dolayısıyla çekinti eğilimini arttırır. Onun için onu baz metale göre değerlendirmek lazım. Bu da aslında termal analizle mümkün olan olur. Teorik olarak baktığımızda baz metalde bazen öyle bir noktaya yakalanabilir ki dersiniz bunun aşılamaya ihtiyacı yoktur. Ama mutlaka bir miktar aşılama yapmak gerekiyor. Hiçbir zaman standart aşılama şeyde aslında doğru değildir. Bunu termal analiz yöntemiyle belirleyip ona göre aşılama yapmak en doğru yöntemdir.
Okay, Katrina, the last question to yourself again, because we have already exceeded the allocated time limit there. The question is coming from Oğuzhan Atlahan. He is asking which inoculant, when, and at which ratio should be used. So this criteria, how can we create a kind of criteria part-based in our foundry? What should be the criteria there?
Yeah, so this can, I think this needs some more specific discussion with Atlan, because it depends on the part. But you would have to start with getting data on the nucleation potential, and then knowing what kind of parts are we talking about, what are the section sizes, and the process. So to give a better answer to this. So are we talking about thin section or thick section? That will then have an effect on what answer to give. Is it gray or is it ductile iron? Is it high, for the gray iron, is it high carbon or low carbon equivalent? So all of these things would play a role in the recommendation. So cannot give a specific answer to this, but we would have to start with looking at the process and discussing in detail. That's my answer there.
Yeah, I'm sure RFP is paying regular visits to their foundry in Ala.
Oğuzhan Bey sanırım zaten Oğuzhan Bey evet. Ya aslında yani dediğim gibi tamamen baz metale bağlı her şey. Baz metali kontrol altında tuttuğunuzda ona göre hangi aşamada ne kadar aşılayıcı yapacağınız konusunda daha net bir fikre sahip oluyorsunuz. Dolayısıyla çekirdeklenme potansiyeli, Tretman'ın de dediği gibi çekirdeklenme potansiyeli önemli. Çekirdeklenme potansiyeli düşükse o zaman daha fazla aşılayıcıya ihtiyaç duyuyor. Mesela bunun alt öteklik sıcaklığı 1140 derece civarında ve üstünde olduğu zaman bu iyi çekirdeklenmiş bir baz metal anlamına gelir. Ve bunun altındaysa o zaman baz metali iyileştirmenin yoluna bakmak lazım ki ona göre bir sonraki aşamada kullanılan aşılayıcıyı da o belirlenen oranda vermek gerekiyor. Dolayısıyla aslında tamam her şey baz metale bağlı dökümde.
The second part of Oğuzhan's question, Oğuzhan is asking another question, similar question. What is the effectiveness of the inoculant which is added into treatment ladle, nodularization ladle?
Yeah. Typically, when you add it in the treatment ladle, or in the case of ductile iron treatment, we recommend that you don't add it together with the treatment, that you add it to the last third of the metal going in. Then you will have an effect, but it will not be the full effect as if you were adding it as a separate stage. So we count that you maybe have 2/3 of the effect if you're adding it in the treatment ladle. But it can have an effect on the nucleation. It does, but it's not the same as if you're keeping it as a separate step.
Arif Bey, ne demek istersin bu konuda?
Ya, şimdi aslında Katrina'nın demek istediği hiçbir zaman aslında ön aşılama çok tercih edilen bir adım olmaması gerekir. Nihai aşılama her zaman tercih edilmesi gerekiyor. Çünkü sonra aşılayıcıların hepsi çok hızlı bir şekilde etkisini kaybederler. Dolayısıyla kalıba dökmeden önce yapılması en sağlıklı yöntemdir dökümde. Tabii ki potaya verilenlerde bir katkısı yok değil. Yani biz saha tecrübelerimizde de termal analiz ölçümlerimizde de bunu görüyoruz. Ama nihai olarak en sona verilen aşamadaki aşılayıcı kadar ön aşılayıcıların bir etkisi olmuyor maalesef. Yani çünkü çok çabuk etkisini kaybediyor.
Evet. Şimdi biz bütün konuştuk.